I welcome you all for this NPTEL lecture on earthquake resistant design of foundation. This is 25th lecture and we continue with pile foundations. Let me share the slides with you. So you could see that in this lecture, we are going to talk about design of piles in liquefiable soils. So this will be first lectures of design of piles in liquefiable soils. And uh, as this is part of the third module of this course, which is on pile foundations. And in this case, this is the last part of this third module, that is design of piles in liquefiable soils. Just before this, we have already discussed two lectures on CPRF, that is combined pile raft foundations. So today we are going to start the design of piles in liquefiable soils. And as you may be aware, this is a very important topic, because when the piles are passing through the liquefiable soils, then its design is really complicated and difficult. So today's lecture is in that direction, that suppose if your soil is not normal soil, or it is not that some of the soil layers can liquefy, how you will deal with that. So that we are going to discuss in today's lecture. And before I go ahead, let me acknowledge that most of the contents of this lecture is taken from the book, which is entitled as Design of Pile Foundation in Liquefiable Soils, published by Imperial College Press, and the authors Madhubashu et al. Are there. So speaker is grateful to these authors for providing such a good the literature, where this book is completely on dealing with the different piles, single piles as well as pile groups passing through the liquefiable soils. Now, continue with that. Let's discuss that what are the contents of today's lecture. So when we talk about these contents, what we are going to talk, design of piles in liquefiable soils, that is the lecture 1, and perhaps we'll discuss another lecture on the same topic. So we are going to talk about introduction, that what are the case issues. And second thing, performance of pile foundations in past earthquakes, that how they have performed, particularly what are the failures of those foundations due to liquefaction or due to shaking, that we are going to discuss. The next is modes of failure in liquefiable soils. When we talk about modes of failure in liquefiable soils, it will be covered into two parts. One is failure mechanism for single pile, and the second is same failure mechanism for pile groups. So let's talk about introduction. When we go for introduction, we will have brief introduction about liquefaction. What is liquefaction and how it works? We are going to talk about that, because this course is on earthquake resistant design of foundations. Those who are already familiar with the liquefaction, they may be that this introduction may be review for them. So what happens during, that liquefaction is a phenomena which is normally occurs in saturated loose sands. So naturally, for liquefaction, it is necessary that there should be some water inside the soil. If there is no water, then the liquefaction is ruled out. So water is there, then the soil should be saturated, and it happens in loose conditions. If it is already in dense condition, then chances of liquefaction decrease drastically. So coming to the introduction part, it is here. When loosely deposited sandy soil layers are subjected to shaking from earthquake loading, the soil grains tend to reorganize into dense packing, thereby exhibiting a volumetric contraction. So what it says, then due to shaking, which occurs due to earthquake or that, what will happen if it is soil condition is in the loose condition? It will try to pack the particles, and once there will be dense packing, then what happens if the soil layers are fully saturated? Then whatever contraction tendency of the soil layer, it will be manifested as rise in the pore water pressure, as there is insufficient time for the pore water pressure to escape from the soil layer. All right. So in this slide, there is a difference between first and second case. Suppose you have loosely deposited sandy soil layers, which is in dry condition. So once you apply the earthquake loading, then what will happen? Soil will get densified. There will be no liquefaction, and there will be change in the volume. Volume of the soil will decrease. But if you have water inside the soil, and when you provide some shaking to that, then there will be rise in the pore water pressure. And this rise in the pore water pressure, if you have you have the effective stress is nothing but total stress minus pore water pressure. When the pore water pressure rises, the effective stress of the soil decreases, number one. And you may be aware that when we talk about the soil, the shear strength is the most important parameter of the soil, right? If I ask anyone that what is the most important property of the soil, it is shear strength. And shear strength is a function of what is called effective stress. So effective stress decreases due to increase in water pressure. And when the effective stress decreases, then there will be decrease in shear strength. And shear strength, if is completely become zero, that case this will be soil will behave like a fluid, and when this behave like a fluid, that case what is we call it is liquefaction. If the excess pore water pressure increases sufficiently to match the effective stress in the soil, then it is said that soil layer is fully liquefied. What will happen? That if pore water pressure is reaches to such a condition that its effective stress becomes zero, then we say it is fully liquefied. But sometimes there is increase in excess pore water pressure, but still the effective stress is not fully zero. In that case, what we call it is the shaking is limited or what maybe other reasons, then still the soil will soften, though it will not be fully liquefied, then soil is said to have partial liquefaction. We can say like this: if effective stress becomes zero due to increase in pore water pressure, then you can say it is liquefaction. However, if effective stress gets reduced due to increase in pore water pressure, but it doesn't become zero, then we can say that it is classified as a partial liquefaction. So this was background about liquefaction. Now continue with that. What is its effect of liquefaction on foundations? How does the liquefaction affect the foundations? So normally, the foundation of civil engineering structures suffers settlement or rotation when the soil layers suffer liquefaction. So during the liquefaction, if soil layer get liquefied, that case there will be settlement or rotation, it will increase. And pile foundations can be particularly vulnerable to soil liquefaction. If the soil below the base of the pile becomes liquefied, then there is a decrease in the base capacity. The pile can suffer excessive settlements. So as a result, due to liquefaction, what will happen? The capacity of the base capacity will decrease, and normally settlements increase. Due to liquefaction, bearing capacity of the foundation also get decreased, as well as there is increase in settlement. But settlement is a major issue, which is becomes so much that this is beyond the permissible settlement, or it becomes a definitional settlement. So due to the liquefaction, the settlement becomes a bigger issue than bearing capacity. And most of the failure which have been seen in the past earthquake due to liquefaction is due to excessive settlements. If the depth to which soil liquefies is rather limited, say in a relatively small magnitude earthquake, the soil surrounding the shaft may liquefy and loss of shaft friction may be expected. As a result, this will cause an increase in the base load of the pile, which can lead to an increased settlement. In addition to these simple cases, pile foundations are also vulnerable to laterally spreading ground. So first of all, there is increase in settlement, decrease in bearing capacity, but there is another term which is given here, lateral spreading. In the last line, you see that there is one thing, lateral spreading. So lateral spreading is also a phenomena which is related to liquefaction only. Okay. And this lateral spreading is mostly occurs in sloping ground. In a level ground, you may have liquefaction, but when liquefaction occurs for sloping ground, then it could be related to the lateral spreading. So as mentioned in the slide, lateral spreading of sloping ground can occur if the soil layers suffer either full or partial liquefaction. When excess pore pressure is generated in the sloping layer, the slope may no longer be able to resist the static shear stress and it can start to flow. Soil foundations that are passing through a laterally spreading ground will be subjected to lateral kinetic loads. Generally, if the soil layer has fully liquefied, then the lateral forces exerted on the piles by flowing ground may be considered to be relatively small. However, if there is a steep soil layer above the liquefied layer, such a layer would also spread, and these non-liquefied layers can exert large lateral loads on pile foundations, as they are able to generate significant passive pressure against the piles or pile cap. So the last paragraph is means if you have a, let's say, a number of layers, what could happen? Some layer get liquefied, some layers do not liquefy. So that is also a dangerous case, because those layers which are not liquefied, non-liquefied layers, they will exert large lateral loads on pile foundations at the junction. And these things we are going to discuss in this lecture in very much detail. So all these things will be cleared once we discuss further. So before that, let's discuss what are the performance of piles in past earthquake. And this slide, and let me acknowledge again, this table is taken from the literature which has been book by Madhubushi et al. This is taken, this table as well as figures in this lecture is taken from that. So we acknowledge that. Here, performance of piles in past earthquakes has been given, and all these earthquakes, which is 13 earthquakes here, is taken from Japan, and out of that, 6 are from Kobe earthquake, and 5 reports are from Niigata earthquake. Niigata earthquake is 1964 earthquake, which and it is very famous for liquefaction. You may be aware that in 1964 there are 2 earthquakes worldwide. One was in Niigata, which occurred in March, and then another was in Alaska, which occurred in. So you have in the same year 2 major earthquakes worldwide. One is in Japan, another in USA. At that time, these was 2 largest economy of the world, and in both the earthquakes, a lot of liquefaction occurs. That's why the worldwide studies started after 1964 on liquefaction. So you can say, of course, people know about liquefaction before 1964 also, but these after Niigata and Alaska earthquake, the studies on liquefaction pick up on worldwide. You could see that in this table there are numerous examples of Niigata earthquake. Number 1, number 2, then you could have other number 8, 9, 10. Then another earthquake occurs in 1995, is Kobe earthquake, and during Kobe earthquake also there was a lot of liquefaction, and there are many examples here in this table related to Kobe earthquake, number 4, 5, 6, 7, and then 12 and 13 also there. In different examples, what is observed? The diameter of the piles are given, length of the piles is given, it is listed is lateral spreading observed. You could see in all the cases, yes, lateral spreading was observed in all 13 cases. Okay, that means because there was you have sloping ground, then lateral spreading, and the sloping ground can occur whenever near particularly seashore. The last column of this table lists how was the performance of piles. So in some cases it was good. On the left hand side it is good, except number 2. But if you see in the right hand side, it is the other way. Number 7 is good, but performance for the other 6 cases it is very poor. So in the past, when we see the performance of pile foundations, when the piles are passing through liquefiable soils, then it has been observed that piles perform very good, or they have performed poorly. So both experience are there. It is mixed experience, good experience as well as bad experience. Both experience are there from the past earthquake. Now coming to this, we are going to discuss that how pile foundation performs in past earthquake. Again, as I mentioned earlier, these all photographs are taken from the literature, that is from Madhubushi et al. It is acknowledged, and this is everything is there. So speaker acknowledged that this is not our material, rather it is taken from that literature, including these photographs. What you have here, in this case, in this photograph, what has been shown, I can explain it, that this is the collapse of Showa bridge. Okay, and this when you have this collapse of SOA bridge, you see that the span of the bridge, many spans have inside the they have gone inside the sea. But what you could see here that the in this figure on the right hand side, this pile foundation is shown. Because this bridge was situated on the pile foundation, there is pier and below you have piles. What you have, there are different spans. You have AL is abutment, left abutment, P1, P2, P3, P4, P5, P6, P7, they are the piers. Okay. You see that there is a span G1 and G2 is fine, but G3 collapse, G4 collapse, G5 collapse, G6 collapse, G7 collapse. So many 5 spans of the bridge got completely collapsed. As a result, this bridge is declared that this is almost completely collapsed. This was the performance of pile foundation in Niigata earthquake. So that means it was not good. If you see this Showa bridge, I think this is listed here. Showa bridge, so the performance was poor in the second case. Okay. So, and the pile diameter was 0.6 and pile length was 25 meters. So it was 60 centimeter pile, diameter pile, and length was also quite high. 25 meters is quite good. So the performance of pile foundation during Niigata earthquake for the Showa bridge was not good. It is poor performance. Continue with this. The next one. Continue with Niigata earthquake itself. And this is pile foundation for Niigata family courthouse building. So that has been also listed here. Niigata family courthouse buildings is here. See here. May not be here. This is from Niigata earthquake. So you have in this case what you have on the left hand side the details of the piles are shown. There are 2 piles, number 1 pile and number 2 pile, right? And then the soil profile is given here. What is there? This shadowed is as liquefiable layer, which is quite deep. What you could see in this case, N values are varying 10, 20, and this is water level. So below the water level, because above the water level there is no point of considering liquefaction. Below the water level, where the N values is less, liquefaction occurs. And when we say N values is less, even N value is high at a depth of 8.5 meter or so, still it gets liquefied. And then it is drastically when N value. So you could see the for the liquefiable soil, the value of N is somewhere between 5 to 15. It is at everywhere more than 5, but N5 is nothing. You know, if N value is less than 10, then soil condition is not good, and certainly it is expected to liquefy. So when N is 5, then you have 10 and 15 and 20. What you have here, N values here, continue. So it start increasing from here, but because depth is so high, requirement is also high. But after when N become more than 15, then this the possibility of liquefaction is ruled out. This layer from almost from 1.5 meter to 8.5 meter, that means about a depth of 7 meter get liquefied, and this liquefaction caused problem to the piles. And the damage to the piles has shown on the right hand side. What you could see that this A part is showing upper part of pile 1, okay, damage here, and lower part is shown as a pile 2. This is here. I can pull that pointer here. So this case A part is here, which is showing the details of this portion. While B, this is corresponding to this. Lower part of pile 2 is shown here. Okay, and upper part of pile 2 is shown here. The third one here. This is denoting this part. Right? So you have so many there. What you could see here, that there are damaged pile 1 at top part, well pile 2 get damaged in part 1 as a top part as well as lower part also. So the performance was not good for pile foundation. Continue with that. So then you have effect of lateral spreading on piles and pier in Niigata. This is the bridge you could see. It appears to be intact, but later investigation, these this is a view of PSC in laterally spreading soil. So when we say laterally spreading soils means there is a liquefied and there could be some slope. It is a gentle slope. It may not be leveled ground. Then you could see that this is the systematic diagram where failure mechanism is shown on the right hand side by formation of plastic hinges in the piles and the pier. So here you have plastic hinge in the pier, right? Then you have the plastic hinge here. Then here plastic hinges are there. Then down also. So many plastic hinges is made. 2 locations in pier and 2 locations for each pile. So there is a pile group. Here it is 2 piles shown here. What is the soil ground? You have liquefied sand here. Top layer is not liquefied. So and then lateral spread. So what you have? This is pile cap, right? Pile cap is embedded at the junction of liquefiable and non-liquefiable ground. Okay. So these plastic hinges get formed. As a result, the pile foundation get failed, piers get failed, and this was the landing bridge. So performance was not good here again. This mechanism we are going to discuss in detail when we discuss the mechanism of single pile and pile group. Now continue with that. Effects of liquefaction on pile foundation during 2001 Bhuj earthquake. So what you have here in the Bhuj earthquake, what you have, this is the case there. So you have a view of the old berths with battered piles here. Then you have new berths with still encased concrete piles. So it is at A and B. And then what is at the, you have subsidence in the cargo handling area behind the new berths. So this is, picture is from 2001 Bhuj earthquake. That is from India only. So you could see that in this figure, what has been shown is the first case, it was the old construction. In the second case, new construction. And third is showing the position of the soil behind the new berths, so under the cargo handling area. And this is soil profile. When we talk about soil profile, you have soft plastic clay on the top, silty sand, and reddish clay. So for liquefaction clay, there are no chances of liquefaction. Rather, they can lose their strength. But this silty sand is certainly liquefiable. So if there is water and if it goes under to go shaking due to Bhuj earthquake, then this layer may get liquefied. As a result, there was damage in the Bhuj earthquake. There was some damage to pile foundation in Bhuj earthquake. Now coming to the second part of the lecture, today's lecture, let's discuss failure mechanism for single pile in liquefiable soils. We are going to discuss only single pile right now, and then we will discuss, once we complete it, we will discuss pile group also. So first of all, single piles are with small pile caps are usually used to support individual column. That means normally, the pile foundations are used in the group. But sometimes it may happen, suppose you want to support an individual column, then only one column is there, then it is possible that if you have a higher diameter pile, then it could be a single pile also. Firstly, the case of a single pile level ground is considered. That means the ground condition is considered level. 2 possible mechanisms of failure can be readily identified as shown in figure 1.1. You could see here in the figure 1.1. Let's discuss this and we will come back to that slide. Here, in both cases, pile is same, identical pile both the cases. Load applied on the pile is also same. But what is the difference? There is a difference in both cases in the soil profile. Here you have liquefied sand. Here also you have liquefied sand. But the tip of the pile is socketed inside the rock in the first case. While in the second case, the tip of the pile is inserted in the dense sand. Okay. Now, because here you have a rock, so once you have the rock, it will support the pile. It will provide a good, it will provide you a very good base stratum. And when the load is applied, so pile becomes kind of a fix here at the pile tip. So when this axial load is applied, then it will move, and it is called what is called buckling instability. This will buckle. First case, the pile will get buckling. While in the second case, when you have dense sand, because when the liquefied sand liquefies, then it will penetrate to dense sand also, and there will be decrease in strength of dense sand. When you apply axial load, compressive load from the top, then the pile will go inside the sand. That means it will be going bearing failure. That means it will move from its position. So the pile will not be at its place. Once this, what we are discussing is here the effect of liquefaction. See, if there is no effect of liquefaction, you have the solid line. Rotated line is the case when the top layer gets liquefied. In both the cases, when it gets liquefied due to liquefaction, first case pile will get buckled, while in the second case pile is not buckled, rather it is going penetrating inside the dense sand. These things has been discussed in the last slide, and let me explain it further. So the single pile carrying large axial load from the superstructure and located in loose liquefiable saturated sandy layer overlying the bedrock is present. This is the condition. That means you have a soil layer which is loose, liquefiable and saturated sandy layer which is on the top of a bedrock. When the earthquake induced cyclic shear stresses lead to the generation of excess pore pressure in the sandy layer, the stiffness of this layer degrades significantly. And under these circumstances, the single pile can suffer buckling instability if sufficient length becomes unsupported and can fail by forming a plastic hinge. Okay, so what you have, this is unsupported. What will happen? So in the first case, why this pile gets buckled? Because this pile is not getting, let me pull this pointer and here in this case, okay, this is the portion where there is unsupported. Support of the soil is not available to the pile. As a result, pile move in the right hand direction and it gets buckled. Okay, so this is unsupported length is there. As a result, the initial position of the pile is shown as we already discussed, and the dotted line is showing anticipated failure mechanism. Here one need to understand the location of the plastic hinge shown in this case. So what is this? This is plastic hinge. Plastic hinge is made at this point. All right. So there is a formation of plastic hinge in the first case, but there is no formation of plastic hinge in the second case. Now let's discuss the second case, which is when the bearing failure. In this case, in contrast to the case which we have discussed earlier, the single pile carries large axial load like same as before and passing through the loose saturated sand rest in the dense sand. It is resting in dense sand layer. Earlier was resting on a rock. The loose sandy layer will again see a significant rise in excess pore pressure and the degradation of soil stiffness. So as when there is a liquefaction, there will be increase in pore water pressure as well as degradation of the material. And this excess pore water pressure generated is close to the interface between the loose and dense sand layers and transmitted to the dense sand layer. So the issue is there, when being the dense sand layer, the effect of this liquefaction will penetrate this dense sand layer also. This will be penetration will be also here at the junction. The effect will be not only lying. In this case, effect was only a full liquefied sand because there is a rock down there. But here, dense sand also lose its strength. Dense sand may not liquefy, but it will lose its strength. There is increase in pore water pressure. So as a result, the dense sand will soften, and this situation will lead to following two conditions. What are the conditions? There will be loss of sharp friction of the pile and reduction in the bearing capacity of the pile. You know, when we discussed the pile foundation earlier, the total load of pile foundation comes from two angles. One is coming from what is called skin friction, another is called end bearing or point bearing resistance. So here, both point bearing resistance and skin friction decrease. Why point bearing resistance is decreasing? Because the dense sand also loses its strength. Skin friction get decreased because this layer get liquefied. So both things will happen. And under these circumstances, the pile foundation will suffer a bearing failure and will settle into the dense sand layer as shown in figure 1.1b. In this case, here this was buckling instability. Here this will settle. You could see the solid line is the case, earlier case, while dotted line is the case after liquefaction. So this is going down, and this is, there is a problem of settlement as well as the problem of bearing pressure. And further, the dilation of the dense end layer will generate large suction pressure in the dense end, which also adds to the process of reaching a vertical equilibrium. Because what will happen? The dilation means, because when you have the loose condition, loose sand, when you apply some load to the loose sand, then what will happen? When you apply the load to the loose sand, then soil will be that contracting. But when you apply the load to the dense sand, then it will be expanding, dilating, those phenomena. So this dilation will also lead to it will also add to the failure condition. So this was the case when you have two layers of the soil. One is the liquefied sand layer and below the non-liquefiable. So in this profile, we have considered only two layers. In one layer, you have liquefaction, and the below down layer, you don't have liquefaction. Now let's consider a case when this liquefied layer is in between two non-liquefiable layers, and what happens to that? That is shown in this figure. What is shown in this figure? You have non-liquefied layer on the top, which is normally made of clay, or maybe because in the and then liquefied sand is there. So many situations in the top part you have the clay or cohesive soil that may not liquefy, but below depths you have liquefiable sand. Okay, and down you could have dense sand. So this is the similar case as 1.1b, except the difference that you have one more layer here. When you apply the load here in this case, now the scenario is different. There are two junctions, two interface. One interface was as before between liquefiable and dense sand, and another interface junction comes here. Okay, and at this interface is connection between non-liquefiable layer and liquefiable layer. What will happen? That some inertial forces is applied when liquefaction occurs to this layer. Then this top layer exert inertial force on this part of the pile, and it gets buckled. Okay, so this part gets buckled, and at the same time you could see it is settling also. So as a result, in this case, it will be combined bending and settlement failure of pile in laterally spreading ground. Okay, so in this case, the failure is due to both effect, bending as well as settlement. So a commonly occurring field case is when the pile is located in layered ground with non-liquefied crust. These things, what is listed in this slide, we have already discussed. That this is a case for a single pile where a liquefiable layer is between two non-liquefiable layers, and the top layer is not so ridged, but the bottom layer is dense sand where the pile tip is located. In that case, the failure of this single pile will be due to both effect, bending as well as settling. So this was all about single pile. Now let's discuss failure mechanism for pile group in liquefiable soil. This is the third component of this lecture. So we are going to last and third part of this lecture. What you have, let's discuss here also the first case where this pile group of two piles, for simplicity, is passing through a soil profile of two layers, one liquefiable sand and another is rock. And two piles are connected by, on the top of the piles you have what is called pile cap. This is pile cap. Okay, and the load is applied on this pile cap. When the load is applied to this pile cap, then there could be two scenarios. One scenario, you assume that this pile cap is ridged, and when you apply the lateral load, horizontal load to this pile cap in addition to the vertical load, always vertical load will be there. So during earthquake loading, what will happen? This system will be subjected to lateral load here. Let's say if I put here, this will be also subject to lateral. This pile cap can move from its original position solid line to the rooted line. Once it moves, then what will happen? It will try to move this pile also. So what happens? Get this plastic hinge, one plastic hinge, another plastic hinge, which is at the junction of pile cap and the pile head. Okay, and another plastic hinge is formed at the junction of liquefiable layer and rock. So 4 plastic hinges are formed in this figure when the pile cap is just moving in a horizontal direction, but it is not rotating. So pile group in level ground, so there is a 4 hinge mechanism in the first case, while in the second case, when pile cap is get rotate, settle down, in that case, there will be 3 hinge mechanism will be there. You have 1, 2, and 3 hinge mechanism, and when these 3 hinge mechanism are there, what will happen? This is the case when, because this have come down here, so as a result, there will be no hinge will be formed here because this pile is remain at its own location. Okay? It is not moving. Okay? It is not buckling. So buckling occurs only in the second pile, not in the first pile. All these things are listed here, so I can do this again. Deep foundations are more commonly designed with group of piles, which is the case. The failure mechanism for pile groups in level ground are considered. The case of a single liquefiable layer overlying the bedrock is considered. Again, axial load is present on the pile group at the time of earthquake loading. As described before, the liquefiable sand layer will lose its stiffness owing to the generation of excess pore water pressure. Under those circumstances, the pile becomes unsupported and can fail as before due to buckling instability. So you have further mechanism of failure as presented in figure 1.3. What you have here, what is the failure mechanism for pile groups in liquefiable soils? So what you could see here, figure 1.3a and 1.3b. So this thing we have already discussed. Now let's discuss the second part here. So in this case, first part, the pile failed by forming plastic hinges both at the base and the pile heads. This assumes that the piles are well rock socketed into the bedrock. If this is not the case, then pile tip rests on the bedrock, then no plastic hinge will form at the tips. This plastic hinge will form only when this is socketed. If this is not socketed, then we have already discussed in case of single pile that this was socketed in the rock, so plastic hinge get formed. But when it is going to, not in the rock, then there is no formation of plastic hinge. In both the cases here in the group, it is inside the rock, so plastic hinge get formed here. Then, in this mechanism, pile cap will suffer lateral displacement and small vertical settlement that may cause significant distress to the superstructure. In the first case, what will happen? There is a lateral displacement of the pile cap and the settlement, buckling of the piles. In the second case, which we are coming here, a second mechanism that can occur is a 3-hinge mechanism shown in figure 1.3b. In this case, the plastic hinges will form only at the pile heads. One of the piles has to fail by buckling instability, and this mechanism can cause severe rotation of the pile cap, causing significant distress to the superstructure. Also, it should be noted that this mechanism can occur even if the pile tips are well socketed to mobilize full fixity at the pile tips. So this is the case here. So I think it is clear that in the first case, what is the difference depending on the load condition? In the first case, there is a formation of 4 hinges, plastic hinges, and as a result, both piles will get buckled. Once both piles get buckled, the pile cap will slide. In the second case, there is a plastic hinges formed at only 3 places. For pile second, at both cases, but at pile first, it is only at the top. And this is depending on the load condition. Okay, so and this is because this in one case this could be the mechanism of failure, in another case. So either of these could be possible. Once you have, if this is the second is the scenario, in that case, pile cap will get rotate as shown here, right? So this was the case when this pile group of 2 by 2 pile group is passing through the 2 layers. One is liquefiable, another is raw. Now let's discuss the last case for the pile group. When this pile group is passing through the 3 layers, that is rock at the down, then liquefied sand, and the top is non-liquefied layer, then the situation is more dangerous than the earlier one, because at the junction of non-liquefied and liquefied layer, this layer will apply what is we call inertial force to these piles. So there is a pile group failure in lateral with non-liquefied crust on the top. Let's discuss this case. The soil profile considered is the same as before with a non-liquefied crust layer underlain by liquefied sand layer. This is similar to earlier, only the difference that on the top of liquefied soil, we are considering one more layer which is non-liquefiable. The pile group is socketed into the rock. The axial load from the superstructure is present on the pile group at the time of the earthquake loading. The failure mechanism of the pile group is shown in figure 1.4. Large lateral loads will be generated on the piles due to the passive earth pressure from the non-liquefied crust on the piles and pile cap. This is in combination with the axial load can cause excessive bending of the piles, leading to the formation of 4 hinges as shown in the figure 1.4. This will lead to the formation of hinges. This was all about that what we have discussed in this lecture. This lecture was completely when the piles are passing through the liquefiable soil. Let me summarize this lecture. First thing what we have discussed is what is liquefaction. Second thing, we have discussed what are the performance of the pile foundations during the past earthquakes when the piles are passing through the liquefiable ground. The third case, we have discussed the failure mechanism of single piles when they are passing through the liquefiable soils, where we have considered 2 cases, 2 soil profiles. And the last one part of this today's lecture was failure mechanism of pile groups in liquefiable soils when they are passing through the 3-layer ground. And I hope that you will find this is very interesting. Thank you very much for your kind attention.